today. This is our second coffee talk of the year, first of the fall semester. For those of you who don't know me, my name is Chris Shealy. I am one of the instructors in the GIS professional programs, and I am also an alumni of the in-person master's program. And so I've been teaching with the program since its start. I've been involved with helping create some of the course content, so heavily invested and really love this department. And one of the things I also enjoy is networking. And I thought we'd bring back the Coffee Talk series, which first happened back the first year of this program, allowing us to connect different alums as well as current students in the program with each other, because we're all doing really cool things in the GIS and cartography world. And what a better way than to get everyone together, at some frequency during the semester. So I decided to talk to a few people I know, and I'm hoping that we can have some more speakers, next semester, branching out a little bit. But today we have Scott Farley, who is also an alum of the program. Scott completed his master's back in, 2017? In GIS and cartography, working with Jack Williams. He can go into that a little bit more. I'll let him share that. But Scott today is going to talk a little bit about what he's been up to since graduating and doing some really cool things in the space of wildfire modeling. And I'm just really excited to share this with all of you. And so Scott's going to give a little bit of a presentation. That's what the format's going to be. And then we're going to have an open discussion afterwards. And hoping everyone, if you do ask questions, feel free to unmute yourself, turn on your camera. I just want to keep this as informal as possible. This isn't anything that's formal. We are recording this though, so that those who aren't able to join us right now can look at this later. And so thanks again for everyone joining. Thank you, Scott. Thank you, Rob, for helping facilitate this as well. So with that, Scott, I'm going to pass it over to you and we can get started.
Cool. Thanks for having me. I'm super excited to be here today. I have a deck. Can y'all see my deck? Nice. So I'm super excited. I had a lot of fun putting this together. I thought for today we'd talk a little bit about how fires work. This is something that I've been interested in kind of for the past decade. So talk a little bit about how you might approach modeling a fire from sort of a geospatial perspective. Think about some of the challenges to doing that. And then think about how you could judge whether or not you're doing a good job in modeling, which is actually a much harder problem than you might think it is. So we'll go into a little bit about kind of that aspect of things. But really, as Chris said, right, like this is meant to be a discussion. So if we get through the slides, that's cool. If we don't get through the slides, that's cool too. If you want to just spend time asking questions, please jump in. Please feel free to, unmute, turn on your video, all good. We can take questions as they come. So just quickly, let's see, I should present this in slideshow mode. Just quickly, a little bit about myself. So I started at Cal, did my undergrad at Cal, got really interested in wildfires and GIS at the same time, and kind of like the joint interactions between fire and GIS modeling. Came to Wisconsin in 2015, studied with Rob, studied with Jack, and got really interested in ecology and data science, and kind of understanding how we can use large amounts of data and maps and geovisualization to tell stories about data sets, and also be able to kind of understand what a model is telling us and how we can use that model to make better decisions. After finishing in 2017, I went to Mapbox, started out as a machine learning engineer, and ended up managing the search product there. So worked with software engineers to build sort of like a Google Maps style search, right? Restaurants near me, those kind of things. Worked on very, very high volume applications. I went on call, right? Like thinking about how do you make sure that your web applications don't fail. And if they do, you're alerted to it, and that they're very fast and very performant. And so with that sort of background, in the fall of 2020, we had a really bad fire season here in California. And I got thinking, okay, I've got this experience in geospatial modeling, I've got this experience in fire, and I also now have this experience in software and sort of the management side of software as well. So I actually started my own company called Willow with a friend from college. And at Willow, we make fire prediction software. So here's just a quick example of our sort of flagship product that is going to be predicting this fire called the Bolt Creek fire up in Washington. We've got this sort of dark area here is the currently burned, and then we've got a prediction for where that fire is going to be going over the next 48 hours. We've got some additional value adds like looking at for an insurer, where their assets are concentrated, how much risk they're exposed to over that 48-hour time horizon, and things like that. So really been working towards how do you have a very effective fire prediction algorithm? How do you display that on a map? How do you get people to understand those predictions and understand if those are good predictions and really trust those predictions? Because in an emergency situation, right, you really do want to build up that trust and kind of help people understand what those predictions means. So that's a little bit about me, a little bit about the background and kind of where I'm coming from. But now I just want to motivate the talk and kind of like what we're going to go into here. And I think we've all kind of seen images like this, right? Like this is, you look in any newspaper in any summer, really at this point in anywhere in the world, and you've probably seen images like this. And they're really quite striking. But I think stories like this can kind of be a little bit more motivating. So this is a story I like to tell when I'm kind of motivating things about wildfire modeling. So this is a woman named Tamara. She lived in Paradise in 2018. And on November 8th, she woke up to, right, a big fire not far from her house. Within a few minutes, she was literally driving through fire to evacuate. And then by the end of the day, she looked at the news and she literally saw her house in an aerial view from a helicopter, just reduced to rubble, and all of her neighbors, houses reduced to rubble. This is a campfire, and 85 people ended up losing their lives. It cost almost $500 billion to rebuild from. And the thing that's really striking to me about this story is for about the week before this November 8th date, it was very hot. It was very dry. Fire conditions were primed for a really big fire. And yet we still had such a catastrophic and very, very fast moving fire that caught people really unawares. And so these questions are kind of like this question of like, why is the fire so unpredictable? And why can't we do an improved job of making sure that we're ready for that fire when it comes, has really motivated me and my work for, sort of professionally and intellectually for since college. And so spoiler alert, this is what we're going to talk about today, but I'm not going to give you an answer, right? Like there's so many answers to why these things are unpredictable. So I'm going to go into some of the basics, some of the conceptual ways of thinking about this, but like any good problem, right, there's modeling ways to think about this. There's sort of sociological ways of thinking about this. We're just going to take one viewpoint and go over some of the high points. And so with that, we're going to kind of back up here and think about how fires work, right? And so I want you to think about a campfire. If you've ever built a campfire, right, you're going to start with some leaves, some little sticks, right? And then maybe you'll put in some slightly larger sticks. And then finally, maybe you'll put in something that's the size of your finger, the size of your arm, and then finally like a firewood sized piece. And then when you light this, right, like the grass is going to start, this grass at the bottom, it's going to start putting off heat energy. And if that heat energy is enough, it's going to catch those next things, those next bigger sticks. And then those will start putting off heat. And if that's enough heat energy, it's going to start catching those next sticks and so on and so forth. And so really we can kind of make a general statement here that fire is going to spread when the energy of the burning fuel, which you've already got burning, is going to be greater than the energy that it takes to ignite those next pieces of wood. And so really this was sort of formalized in the late 60s and 70s by this guy, Richard Rothermel. And he did a lot of experiments like this. This looks really cool. I would like to do this. But basically he'd go in a wind tunnel and he would burn stuff. And he would draw sort of conclusions about how fast those things burn, what kind of conditions they were burned under, and put together some regression models in very extensive detail about how the fire would burn and what kind of like energy relationships were needed to obtain wildfire spread. This work continues to today, right? Like there's still like sort of this empirical research where there's burn chambers across the country, and people will go and have oftentimes like slow motion cameras to kind of capture these relationships. But this sort of fundamental relationship that we can work with here is this relationship between the fire spread rate, so how fast the fire is spreading, to the amount of heat that the fire is currently producing, to the amount of heat that it would be needed to ignite that next patch of fuel. There's about like, I think 87 different Greek letters. It gets like very complicated, but the whole thing can really be boiled down to something that's like pretty straightforward to understand, right? That we've got this relationship between the heat source and the heat sink. So just to kind of like reinforce that a little bit, right? We'll start out with some of these wood shavings again, right? These are going to have less energy to release when they're burning, but they also take less energy to ignite. On the big side, right, we'll have more energy to release, and we'll have more energy takes to ignite it. So we end up with this sort of inverse relationship between how fast a fire spreads on the y-axis here and how hot it is, how much energy it's releasing on this bottom axis. And so all else being equal, and we'll talk about how things aren't always equal, but if all of the moisture, the wind, the slope, all these things are equal, you might have sort of grass fires, right? Those are going to spread very, very fast, but relatively, they're going to put off relatively little heat. On the other side, right, you're going to have timber fires. These are going to spread more slowly, but they're going to put off much, much more heat. And then, right, you might have chaparral and shrubs and some other fuel types here in the middle, sort of following this inverse relationship. When the fire is burning, we're not going to go into this too much, but I just want to mention, right, like there's a lot of influence of the topography and the wind. These are two, in addition to fuel, these are the two sort of like driving concepts that are going to push the fire in one direction or the other. And really that's because in both cases, the radiative and convective heat that's coming out of the flame is going to be preheating the fuels on the up slope or the downwind side of those flames. And that's effectively going to reduce the amount of energy that you would need to ignite those fuels. So it lets that fire move faster uphill and then downwind. Right, and we can get back to those Greek letters. We can draw some very complicated trigonometric relationships around how that might work with an idealized flame and so on and so forth. But really, again, the concept is these fuels out here are going to be drying out. And so they're going to be able to be released with, ignited with less energy. And then there's going to be able to spread more quickly. So that's how the fire is going to move in one direction. But of course, if we want to know where it's going to be spreading in two directions, we have to think a little bit about what is going to be happening away from, like in all 360 degrees, right, on both the X and the Y axis here. And so in general, your fire, if you have a ignition point here, it's going to be spreading in the direction of the wind and the slope together, right? So it's going to be going, as we said, uphill and downwind. You're going to have a little bit of spread, even so, back in the other direction, back downslope or upwind. And then it's going to create this sort of ellipse. And you'll have a little bit of sideways growth as well. And so if you look at sort of aerial photographs of fire, right, you'll see this pattern. This is why they kind of go in this oval, probably started somewhere around this little farm. It spread out. This is the direction of the wind, and then back towards the heel, and then out towards the side, right? And that's cool if we have kind of one point that's on fire, and that everything else is equal. But again, everything else is not equal, right? We might have different slopes that vary over space, or we might have different winds that vary over space, or different fuel types. And so the way that we can do this kind of in general is by saying this Huygens principle. So this is like, if you think back to your high school physics, right? You might have talked about waves and how waves sort of propagate and maybe they interfere with one another. This principle lets us propagate this fire by using a bunch of these different little ellipses. It's basically saying we're going to discretize my existing fire and we're going to just let it propagate locally. So we're just looking at the wind and the slope vector by themselves for each individual point. We're going to see where the fire gets to, and then we're going to call that the next point, right? So it lets us approach this in a much easier way because we can just worry about the conditions at one point in isolation without worrying about the conditions at every point, everywhere, all the time. So here's an example of that, right? So this is, again, that campfire that we talked about in the beginning. And what we're seeing here is, right, in general, we get this sort of downwind ellipse pattern. But at each point, this fire is going to be moving in kind of the direction that is the local direction of that wind and that slope. And so, right, we've got this little finger of fire over here that's moving as the wind kind of shifts this direction, for example. So this kind of modeling lets us now model in the X and the Y dimensions, as well as that time dimension, because we can propagate this fire front forward. Questions on that? Cool. So what this kind of brings us to is, okay, we know that we can go in a lab and we can like create some empirical relationships for how a fire might burn. But then there's a lot of very challenging sort of technical questions about how you might do this in a GIS or at a sort of a geospatial modeling approach if you want to do sort of real-time fire modeling. And sort of namely the first one that we'll have to figure out is, wow, there's a lot of data that's going to need to go into this, right? So we need data on the slope. We need data on the aspect. And so, right, the cardinal direction of the slope is going to affect how much moisture is in the fuels on like a south-facing slope, right? It's going to be a little bit drier than, say, a north-facing slope in the northern hemisphere. We're going to need to know about elevation. It's cooler at higher elevations than at lower elevations. Of course, we'll need to know what kind of fuel is burning. Is that grass that's going to go faster, or that timber that's going to go slower but hotter? How high is the fuel? How much of the sort of vertical fuel do we have to work with? How thick is the fuel and the fuel canopy in particular? And how much canopy do we have? Is it sort of very sparsely, like little patches of juniper trees like you might have in the Southwest? Or is it like very contiguous, maybe conifer cover like you might have in Montana or Idaho? How does the wind change off of the surface? And right, does it get much faster as you move up in the sort of elevation dimension? Or is that relatively constant? Or is there even an inversion layer where like the atmosphere is going to be moving slower, maybe 100 meters or 200 meters off the ground? That's going to make a difference in how the rest of the weather conditions will evolve. We need to know the solar radiation, right? Is there clouds that are covering the sun that are maybe making these fuels not dry out so quickly? Things like air temperature, of course, and relative humidity, precipitation, right, are all going to affect how dry the fuel is and how quickly it will spread. Again, related to how much energy is needed to ignite those fuels. And then finally, right, we're going to need to know how fast the wind is burning at the surface and in what direction. So like, oh my goodness, this is like so many different layers that we need to keep track of. And they also are going to be evolving at different scales. So of course, we can basically, for our purposes, treat these first couple up here as static. They change over a very, very long period of time. But as we start getting into these vegetation aspects, we're going to be changing over days or maybe months, maybe seasons. And then as we get down into these wind and weather variables, we're going to be needing to have these change every minute or maybe every hour. And so they're much more dynamic. So I did some back of the envelope calculations here, and it's something like 350 to 500 terabytes of geospatial data to be able to have all these layers at all the time, at all the places for the continental US. And of that, about maybe a third to a half is going to need to be updated every 3 to 5 times per hour, right? Like wind speed and wind direction, right? Gusty winds can change every second. If you've ever felt sort of that gusty wind. But if we're thinking about sort of static wind, it'd be nice to be able to have updates maybe twice or 3 times an hour. So that's a huge amount of data. For context here, another back of the envelope calculation suggests that Instagram moves about 500 terabytes of data per day, right? So just to give you a scale, like they're a huge tech company, right? They're moving about 100 terabytes of data around a day. This is kind of on that same scale, technically feasible, but challenging. So once you have the data, like let's just set that aside and know that it's very challenging to do. Just computing these fire spread models is also challenging for a couple of reasons. Many of these models require a supercomputer, right? They're just so computationally complex that you cannot run them on your laptop. You need resources that just don't exist kind of locally. So centers like Wisconsin, centers like the San Diego Supercomputer Center, they run a lot of these kind of high performance scientific computing models for fire. And that's kind of like one of their main purposes. But even with a supercomputer, oftentimes calculating what the next 24 hours of a fire might look like takes more than 24 hours of computing time. And so if you're really interested in predicting where this fire is going, this is not going to be super helpful, right? We're going to be delayed in making our predictions where it actually went. And so there's something like 1 million to 1 billion calculations per time step to be able to propagate this fire front forwards, right? If we're doing it at something like 1 to 5 meters resolution. And many of these sort of contemporary models are starting to take into account how energy moves, not just in the X and the Y direction, but now in the Z direction as well, right? And so as heat moves up, that's going to sort of change where the fire is going and how it's moving, even though sort of the surface fire in the X and the Y direction is kind of moving independently. And so part of the reason that these take so long is they've got 3 spatial dimensions and this sort of temporal dimension. And parallelization here is hard because in order to be able to calculate where we're going next, we need to know where we've been. Right, so if we've got a fire map like this, it's really hard to predict this pink line without having predicted all of the other lines in here, right? Like we would not have been able to predict the pink line just from, say, this first line here, because we need to know all of the local conditions at all of these points along all of these lines to be able to effectively predict how the fire got to the pink line. So we wouldn't be able to say, calculate all of these rings in parallel. We have to go sequentially and sequence through each one independently, which is another reason that it takes such a long time to be able to run this, even if you have access to a really big supercomputer. Then there's a lot of uncertainty. There's uncertainty in how these fires burn. And then a lot of that arises because fire behavior at the scale that you see, say in the newspaper, right? When you see a picture, like we showed at the beginning of like that huge hillside on fire is actually relatively rare, all things considered, right? Like it happens, a few hundred times a year, but that's not really enough to be able to say with a lot of certainty whether or not we're going to see that kind of behavior in any given situation. And so because of that, we mainly test these models and develop these models in the lab, right, in those burn chambers, which are very small scale. And they don't necessarily have exposure to the kinds of conditions that we would see like in the wildland, in the actual fires that are burning. So that's one aspect of uncertainty. Second aspect of uncertainty is how you would even predict winds at a very, very local scale. These fires often burn in locations that are relatively sparsely populated with weather stations and have some of the most complex wind physics, right? So you could think about like if you've ever been up to the mountains, you have a lot of those really gusty winds. These are the kinds of things that are very challenging to model. And there's maybe a lot of uncertainty there. And then finally, wildfires do create their own weather. And so even if you had really good weather station coverage, you might not be able to correctly predict where the fire goes because it's driving itself. And we'll see an image of that here in a second. So first image, I threw this in for Chris because Chris likes tornadoes. Fires can actually create fire tornadoes, right? And so this is super, super rare. And so therefore it's like essentially impossible to predict with a computational model at this point. But it has a very big impact. Like if you do see a fire tornado, that's going to be moving very, very quickly. It's going to be putting off a lot of heat. It's going to have a lot of impact on where that fire ends up going. So if we can't predict this, that's a real challenge to being able to predict where the fire is going. And then in terms of fire creating its own weather, right, what we end up seeing is that the fire is putting off a lot of heat, a lot of the hot air rises, there's a pressure vacuum. And so now you have these sort of fire-driven winds as air rushes in to fill that void. And so you'll often see, if you read stories in the newspaper about how fires are burning very intensely, you'll see, oh, fires create their own weather. This is an example of sort of why that happens. And that today is you're not really able to model that because it is relatively uncertain when that happens or how that happens beyond sort of like the obvious, like you have a pressure vacuum. And so we've got this data problem, we've got this computation problem, and we've got all of this uncertainty and whether or not we're even doing the calculation correctly. But I think it's really interesting to think about how would we know if we're doing the calculation correctly? So like, what does it mean to have an accurate fire model? And so what metric would you measure with, right? Are you measuring burned acres? Like, did you correctly predict the size? What about the direction? What about whether or not structures burned, like did these houses burn when you predicted that they were going to burn, right? There's a lot of different measures that we could use. And under what conditions, right? Like, did we correctly predict the worst case? Did we predict an average case? It's hard to know. And then under what time horizon, right? Did we correctly predict the next minute of fire? Or sometimes these fires burn for weeks. There's a fire in Oregon that's been going on right now for almost 9 weeks. And so did we correctly predict the final footprint after 9 weeks? And so it's not immediately clear which one is the most sort of right to be able to say this is an accurate model. And then there's an extra loop here, which is that we often have fire crews, right? Sometimes dropping retardant, sometimes digging fire lines, sometimes driving bulldozers to like clear fuels out of the way and stop the fire. Do you model the fire with their intervention or without their intervention? And what you kind of end up with is, this is the realistic case where you have the sort of the air tankers interfering in your model, or the worst case where those firefighters aren't there and you get the sort of natural fire behavior. And there's very, very little data on where these crews are operating sort of in real time. And so this adds an extra layer of complexity. So we'll often see, if you go on Google Scholar and you say how accurate are fire models, you'll often see charts like this. And so what we're kind of looking at here is a time series progression of fire shaded here, and then the true sort of fire perimeter drawn out here. This is, I actually don't know what fire this is, but there's many, many studies here that have this sort of same general form. And this is cool, right? Like this makes a good paper, but it doesn't necessarily answer these questions of how accurate is this model in general? How often do we accurately predict, say in the next several weeks? How accurate were we with suppression or without suppression? Things like this. And so I think one of the main challenges is that this is only evaluating in one set of conditions when there are literally millions or potentially billions of combinations of conditions that these models have to operate in. And so one of the things that I've been really, really interested in and have been doing a lot of work in right now is how we could basically take this modeling and make it more data-driven, look at what actually happened in the field and create models out of that. So fire perimeters are updated about twice every day by incident staff. So if you're a firefighter, one of your jobs might be, where is the perimeter of the fire, right? And you might use infrared mapping. So they have a lot of drones working fires now that will take pictures like this. And so white is hot, dark is less hot. And this is the fire here. And from this, you can create a heat map and you can say, here's where the fire is. We also, especially for bigger fires, have a satellite sort of thermal sensors that can give us a sense of here's where the fire is right now. And here's where it's been, the orange is older. So here's where it's been in the past, right? And so from this, you can also, on small fires, you just walk around it and you say, here's where the fire is. So from these combination of methods, you can put together maps that look like this. This is the Caldor fire from last year. And this is the fire perimeter at some point in time. And so we can actually have, this is where, professionals have said this is the most accurate that we can possibly be in saying this is where the fire was at this particular time. So what we could do is we could take that mapped perimeter and we could compare it to what the model says is most likely to happen. And so what I've got here is the black is where the fire was burning at the start of the forecast window. And so we can think about that as 2 days ago. 48 hours ago, it was burning in the black. And then today, the fire actually was burning in the purple. So it grew out here in this sort of floodplain over here. And then at that same time, when the fire was actually here, the model predicted it was out here. And we have a bunch of different lines here. These are different runs, slightly different boundary conditions, slightly different winds, slightly different fuel moistures and things like that. That gives us sort of a set of possible locations that the fire might arrive in at the same time that we have in reality this purple. So right, one of these fire runs is actually way out here. It got really, really big. Some of them are a little bit smaller, right? Like a little bit more in line with what we're seeing with the purple. And so from there, we can say, what kind of statistics can we use to be able to measure, right? We know that there's a lot of different ambiguity about what we might want to measure. So let's try to get a suite of statistics that we could use. And so, right, the first thing that we might look at is forecast area. Did we get the size right? So in this example, right, our best guess was that in that 48-hour window, we were going to get to 1,583 acres. And in reality, the fire only grew to 220. And so we were off by plus 1,363 acres. So that might be good, that might be bad, but it's a data point. We can look at the area that is shared versus the area that is distinct, right? So we shared all 220 of those acres. That's great. But we also missed 1,583 acres, this extra area that is outside of the shared area. And then finally here, we could look at what was the direction of travel. And so in this case, right, we can say, well, actually, we did a really good job of, we did not predict the size correctly, but we did a really good job of predicting the direction correctly. And so we can add that as another data point in our suite of metrics. But what would be really nice is if we had one metric that we could use and we say, here's what it means to be a good prediction. And so what I've settled on after some research is an intersection over union metric, which is basically taking the intersection, this number, the shared area, divided by the distinct area. So here's an example, right? We have two predictions. We take where they are overlapping and then divide it by where they are intersecting. They're not overlapping. And then we can create a single number, which we have here. And this gives us a sense of everything all inclusive. How did we do? And so in this case, we didn't do that well. But again, it's a data point that we can then take and we can measure on many different fires. We can measure again under different conditions if we've modeled something slightly differently and see if we do better in the future. So I do this every day. I run all the major fires in the US 6 times a day. And then I look at their performance every day. And so that's really cool because then we can say, okay, on average, how did we do on a single day? Are we consistent? Is there a lot of variation? There is a lot of variation. I'm not able to explain it right now, but I think that's interesting. We could say, okay, do we usually over predict or under predict? How do we do by state? In California, we do pretty well, but in Colorado and especially Wyoming, we do less well. And so there's all these, we can take all these statistics that we just looked at, and instead of looking at them in one place in one time, we'll look at them holistically and be able to start making conclusions about where models are good and where models need work. And this starts to give us a really rich data set that we could do stuff with in the future too, right? So this is a fire that was burning in Northern California this year. And we can see, again, purple is what actually happened. And orange is what was predicted to happen. So on this first day of the fire, we had a really big run and it burned all this area that was unpredicted. So that's had kind of a different set of intersection that we looked at in the last slide. But then we can track that evolution over time. And so every day we now have a new set of model and reality. And we can see it sort of evolving over this set of weeks. And generally we tend to overpredict that area and not underpredict, although we did underpredict on that first day. And so what we can do is come up now with the potential to have sort of a data-driven machine learning algorithm that learns off of this data, right? We've already collected all of this data. What was the wind and fuel and so on and so forth for this time in this place. Then we have sort of this black box model. And then we can create an estimated daily perimeter, compare it to what actually happened, compute that similarity metric, and then feed it back into our model. So this is very similar to if you have really any kind of statistical model, right? You have a criteria that you're trying to optimize. And then you have a model that learns parameters, whether this is a linear regression between those parameters or like a very complicated neural network, it doesn't really matter. You learn the best relationship between your input criteria and that output that you're using to evaluate. And so the idea here is that we could learn under all of these different kinds of conditions what the best relationship between those conditions are to best produce a fire perimeter that minimizes, well, in this case with the IOU, maximizes that similarity metric, right? And so I think this is like one of the most exciting things that is sort of happening in fire modeling right now. It's mainly academic at this point, but this is something that I've been working super hard on using tools like reinforcement learning to sort of figure out what is that best relationship? How does that actually work? And like, what's the way to learn that relationship once you have all this data, you have all these sort of ways of judging those predictions, and seeing if they're good or not. So that's all that I've got for today. Would love to have a discussion, questions, comments about this or anything else. Also left my email here. So please feel free to shoot me an email if you want to talk about this or stuff that you're working on. I feel like when you leave academia, you kind of like lose a little bit of, just talking about projects. So if there's, something you want to talk over, please feel free to use me as a resource and, let me know.
Awesome. Thank you, Scott. That was super cool. I'm always fascinated whenever you share with me like what you're up to. It always blows my mind. Does anybody have any questions? I have a bunch, but I want to let some other folks ask or go away. So if you don't mind unmuting yourself, turn on your camera, go for it.
Hey, I have a ton of questions. That was actually incredibly interesting to me. I mean, I guess I'll start with a few and then I'll pass it on. If there's still time, I can come back and ask some more questions that I have. But I guess the first one is I'm very curious about the resolution of the data and kind of where you're getting that, because as you were kind of explaining all of the different factors and terabytes of data that you get, like, I'm wondering, like, my instinct is that like the more detailed your data is, the better your model might be. And like, obviously, you're not going to have every single tree mapped out in the wilderness and like how high and how big and how much fill it is. But I'm wondering, do you have any data sources that kind of get you a lot closer to that than what might be publicly available?
Yeah, excellent question. Your hypothesis that better data is better models is spot on, and it probably holds true for like basically anything you'd model. So the sort of like standard US government way, like when you actually like go on a fire and you like start modeling like as part of the incident staff, you would use a 30-meter product called Landfire. It's sort of a collaboration of the USGS and some academic institutions, 30 meters. Which is not quite good enough. It kind of, people realize that like 30 meters is just too big to be able to like map out some of these variations in particularly, like you say, like the individual trees. People are actually trying to map out every single tree. In California, there's a project called the California Forest Observatory that's got, I think it's got now 3-meter data for all of California, and you really do start to see like individual trees. So I think we're seeing a move towards higher resolution data, but the best that you can kind of get at a large scale is about 5 meters, which is still almost too big, but not quite.
I see. And then I'm wondering, like, the other question that I had too was, we were talking about fire suppression. And I was thinking about that too, because oftentimes, you kind of pit a model that maybe doesn't take into account these things, or as you mentioned, like they don't publicly disclose like what fire suppression they're doing. And I suspect that probably has a very big impact on your model. And then also, like, on the flip side, if you were to use this model to try to fight the fires, and to like provide suggestions on like, where do we deploy fire suppression that would save the most lives, or save, something like that. Like, I'm wondering how you think about that kind of issue. I would love to hear a little bit more about that.
Yeah, this latter kind of model that you mentioned is something that I think is really interesting, and have talked a little bit about with folks in the past. And I think using models to be able to figure out not just like where the fire is going, but where the best place to deploy is like a little ahead of its time, but is like definitely the future. I think the real challenge that I have, and I don't have a good answer for your question, so I'm going to like say some things, is that like mainly because there's no data set, and because these models have mainly been built in labs, there's not really a good like sort of mathematical relationship between spread and the presence of suppression resources. at this point. And so I think one of the potentials of having sort of this like big data-driven world of like building a new model is that you would be able to incorporate other data sources and you could sort of build that relationship from scratch. So I think that is an opportunity, but it also means at this point, you're missing a key variable that might be really big. Like hopefully we'd hope the firefighters out there are actually like doing something to stop the fire, right? But we don't actually know that. So it's definitely a big hole in sort of our understanding.
I'll ask one more and then I'll pass it on. I grew up in California, and so I remember last year. I mean, I actually wasn't in California when the sky turned orange. But I guess the other thing I'm wondering is like, do you also model what happens to the smoke and kind of how smoke impacts population centers or things like that?
Yeah, another good question. So I started this company and we were like figuring out like, how do we become a business by modeling fires? And it's quite challenging. We could talk about that separately if you want. But one of the things that we realized was if you're an insurance company, right, like that's where the money is for fires, because you lose a bunch of houses. These companies are willing to pay for better data on where that fire might go. And so, but what we realized is that these insurance companies lose like 10 times more, just property insurance, not thinking about like health insurance, which like would be a whole separate pot, but like just property insurers lose like 10 times more houses to smoke damage than they do to like actual fire, like burning to the ground. So the short answer to your question is it's a really interesting topic that doesn't have a lot of work in it right now. There's not a lot of like sort of operational style models that will model this. But it's really, really complicated. Mainly it's complicated because you now really have to rely on that three-dimensional wind profile. And you need to kind of understand what the large scale atmospheric winds are like, not just the local surface winds. So did a little bit of prototyping, but have mainly focused for my purposes on like sort of the surface fire modeling. I do know that there's a lot of really interesting academic research on those smoke models. And the EPA is doing a fair amount of really sort of like groundbreaking work on predicting for a given fire where that smoke is going to go.
Well, thank you, Scott. Very insightful presentation.
Thanks for the questions. Anybody else have questions?
If not, I have one. I'm just curious, like today, Scott, how are models being used actively in sort of the deployment of resources? Are there models being used or not really? How old are those models?
Yeah, so if you limit yourself to sort of like predicting where the fire is going for emergency purposes, so now excluding like insurance, maybe logistics, there's other places that models could be used. But if you're just thinking about sort of the emergency services sector, models are mainly used to figure out who to evacuate, figure out where to deploy resources, right? Like where do I deploy my firefighter or my jet that's going to drop retardant, and where to sort of set up shop. If you're a fire camp, you end up having to like build this city. So they use modeling to figure out like where the sort of least likely place to be impacted is. Generally, they're using these same kind of models that we talked about. They are running, there's a push towards now being in the cloud, similar to kind of the screenshots that I showed before, but very much like you're running on your like field proof laptop. You take it in the case and it's got like the shock proof briefcase and stuff, and you've set that up in your sort of fire city. And so they're mainly run by these firefighters that are working in the camps on these sort of like emergency activities of evacuation and deployment.
Scott, I had a quick question then. Super cool presentation. And I guess I'm curious, maybe follow on to some of the comments about interventions and, evacuating people. Is there some bias in the models towards those areas? Like, will they maybe overpredict a fire going in that direction if it's in the vicinity of, a populated area?
It's a good question. So mainly these models would, like, at least in theory, be independent. Like there's no knowledge of the model that the model has about going to a population center, right? Because of how they're trained on sort of this like lab source data, if you will. I think if you move towards let's just use the data that we can observe from space or from drones and like build a model off of that, like we're talking about in the latter half, I think you might actually see sort of the opposite. You might see the opposite is happening, is that there's a bias away from population centers, mainly because if the firefighters do get in there and they're dropping retardant or they're performing other suppression actions, you would observe a trend towards the fire is going to stop before it gets to the population center, and they're going to, if given a choice, they're going to let it burn away in the other direction. So I think that evaluating that kind of bias is a really interesting perspective I haven't thought about, but probably makes a lot of sense, right? If you have that sort of like, here's all the ways that I evaluate myself on these fire predictions, like having some kind of bias metric gives you another way of saying, I feel good about this prediction or I don't. Haven't thought about that much.
Awesome, thank you.
I've been thinking about this kind of modeling a lot in more of the preventative side, and wondering if you've seen any work on the kind of cost benefit analysis that this modeling could do for fuels reduction. And that I'm in Oregon, so I'm watching the smoke from the Cedar Creek fire every day. So a lot in my mind about it.
Nice. Yeah, so my job is kind of split in two right now. It's developing the software platform that's sort of the next 72 hours that we saw at the beginning. And the other side is very much on the preventative. How do we use models to do better, in most cases, like public spending of fire department money? So work with some agencies here in the Bay Area. So I do a lot of this kind of modeling for preventative work. And I think it's really powerful to be able to tell the story of like, here's how your money was spent, right? Like you had dudes with chainsaws, like in your backyard, you spending your tax dollars for months, but like, here's what you get instead, right? And so I think there's a real challenge to communicating the value of prevention. But if you are able to use this kind of like data-driven way, particularly if you start getting graphics and charts in there, it becomes a whole different ballgame to being able to like show impact. So I would say for me, like the biggest learning has been really around that, like almost like data storytelling with these models. Like the models themselves are very helpful, but being able to show the spatial impact has been huge.
I guess related to that, I'm curious if you ever team up with, like prescribed burns to kind of model what a prescribed burn might look like.
Yeah, fascinating. I've not done a whole lot, but we have a potential project to do this winter where we would look at, earlier this summer, New Mexico had a really, really bad fire season. And part of the reason it had a really bad fire season was they had two separate escaped prescribed burns. So there's a lot of interest, like everybody loves prescribed, well, not everybody, many people love prescribed burn, right? There's a fair amount of controversy over it. And so one thing that you could use models for is to look at how the fuel changes with prescribed burn. So that's an interesting way. But the other way that people are really interested in right now is my containment plan for this prescribed burn likely to hold? And so oftentimes, right, they'll take their like really big industrial lawnmowers and they'll draw a containment line before they even start the burn. And so using these kind of spread models to help understand, is it likely to hold in that predefined containment area, or is it likely to escape? And like, should I change my plan or make that wider, something like that? So that's something we may work on in the spring. And there's a lot of people that want prescribed burns, and there's a lot of people that don't want prescribed burns, mainly because of the potential to escape. And so being able to answer that question is super important.
I know we're at time here. I just had one final question. So I kind of tie it back in. What has been or maybe give me a couple examples of technology that you've used on the spatial side, either libraries or packages, preferably open source, that you've kind of leveraged in your work so far?
So I do everything kind of from scratch in Python. So from scratch, like basically means like GDAL, Ogre, right? Like those kind of tools are like super useful to me. I think the other thing that I would mention is like just the amount of like data infrastructure out there is massive, right? For being able to access spatial data. So like I sidestepped the question of having to move around 100 terabytes of data 5 times an hour by using government WMS services that do move around 100 terabytes an hour. And so, and then I just take the little piece that I need and then take that into my model. So I'd say like those kind of like open technologies, they're not always like super reliable, but like they do help quite a bit. And then on the data viz side, I'm a big fan of Mapbox. Obviously, I have a little bit of bias there, but I do think you can create really easily a lot of those really nice data visualizations. So every time I make something, I find that it turns out really well there just by basically having a server that produces GeoJSON and like plopping that onto my Mapbox map. And yeah, feel free if other questions come up or you think of something, like feel free to email me and be happy to get back to you.
Awesome. Yeah, thanks again, Scott. Oh, go
Yeah,
ahead.
please go ahead.
It's more of a personal one. I found this Zoom on Twitter. I'm actually a current master's student at University of Texas, and I just started a month ago. And my goal is to look at the Calf Canyon and Hermit's Peak fire to see either controlled burns and like what went wrong and like what we can do about it, or on the flip side, like how to deal with, I guess, like flooding and landslides. And I was just hoping for advice because I feel like I keep finding all of these Zooms and they're really cool, but also half of it goes over my head. And I'm only a month in and it just seems like this is a dream to keep studying it, but maybe I'm just like, I don't know if I'm cut out for it. So hoping for advice.
I would say no matter what, stick with it, right? Like that's kind of like generic advice, but like it's gonna be like you'll get there for sure. Like I think the first week of a graduate program or like first month of a graduate program is like super hard. There's like a lot going on for sure. So like just hang in there generally. But I also think that like as a student, you're in like a really wonderful position that at least I didn't recognize when I was in grad school, of being able to do like these really, really cool things. Like, so for example, I would love to go study like the Calf Canyon and the Hermit Creek fire, right? But like, you don't necessarily, unless you're in that sort of place where you can go work on these things with people who do this professionally, have that opportunity to just go do that. So like, I would say my second piece of advice is like, go explore those opportunities if that's what's interesting, because this is a really great time to be able to do that. And you have like, especially like where you are, right? Like that's a really amazing institution that has a lot of resources that can help you achieve like what you're interested in.
Awesome. Thank you.
That's awesome. Thanks for joining, Catherine. And feel free to spread the word. We're trying to, get this out. This obviously, we want to open this up to a larger GIS cartography community. So yeah, that's awesome that you found it on Twitter. Marketing work, all that.
Yeah, I'll definitely share it with my department. They already know I was going today and I'm supposed to report back to tell them how it went. So I'll say good things.
Excellent. But yeah, thank you everyone for joining. Thank you, Scott. Like you said, if you want to reach out to Scott, he's put his email in there. Our next talk is on November 16th. We're going to bring in Jake Cruz, who's one of our grad students in Songs Lab. And I thought it would be timely as the midterm elections will have happened at that point. Jake does a lot of work on spatial analysis around boundaries when it comes to different jurisdictions. So he's going to talk a little bit about the spatial analysis work that he's been doing there. So thanks again. We're going to be posting this lecture, the link, so that other folks can watch it on Slack and tune in for more. So, thanks.
Cool. Thanks, everybody. Bye.